going to start the recording now and turn it over to Alice Howard to introduce our speakers for tonight.
Well, thanks, Jim. I'm pleased to welcome so many of you to the second of our bonus summer lectures, and I hope everybody, you and yours, are all well. Our regular lecture series begins in September, and these talks will be devoted to exploring some conservation issues, and until further notice, they'll all be on Zoom. We'll begin with one on climate change, and some others will be about wildlife conservation, water resources and air quality, flood management, clean energy, and so on. And they're all listed on our website, but of course we'll be telling you about them as they come up. And while our lectures in the past have been on the second Thursday of the month, beginning in September, they will all be on the third Thursday. So tonight's speaker, Bill Kelly, is a retired New York State geologist. He will talk about the overall structure of the Taconic Mountains with an emphasis on the rocks that comprise the Rensselaer Plateau. This talk was actually the first lecture that began the RPA lecture series some 5 years ago. And we are pleased that Bill has agreed to present substantially the same talk once again. Many of us, including me, missed it the first time, and others are looking forward to hearing it once more. So now I'm pleased to introduce tonight's speaker, Bill Kelly.
Thank you, Alice. That was most generous of you. Good evening, ladies and gentlemen. This is the first time I've done a webinar like this, so we'll see how this goes. As you can, if you're all looking at your screens, the title of this was the Geology of the Rensselaer Plateau. But if we just talked about the geology of the Rensselaer Plateau, we'd be out of here in 3 minutes. What we're going to do is, as Alice indicated, we're going to talk about the Taconic Mountains more or less in general, the rootless Taconic Mountains and the lost oceans that collected the sediments that made these mountains, and then what happened to those things. So we'll be expanding out a little bit from just the Rensselaer Plateau. However, we're going to talk about the Teconics in the vicinity of the Rensselaer Plateau up here in sort of east central New York. More about that later. But anyway, let's get going. Okay, just to keep us oriented as to where we are, Long Island down here, Lake Ontario, St. Lawrence River up there, Lake Champlain through there. And then we'll get the next little bit here will show us a 95% correct map of the general geographic regions here. A, the Adirondacks here through here, an entity unto themselves. The Catskills here, C. The Hudson Highlands, H. The Whites over here in New Hampshire. And then we have separated out here the Green Mountains, the Berkshires, and T for the Teconics. But if you look over here, you're looking at, if you kind of compare that green and pink color, it all looks like one great big thing. I mean, if you drive the Mass Pike from Albany over here to the northern Connecticut Valley, you go uphill, you go through a bunch of mountains, and you come down. And yet this map seems to indicate that there's two separate entities here. There are, but it's very difficult, really, just as you're driving along, unless you know what to look for, to actually say, well, here's the Teconics and here's the Berkshires. They all kind of geographically blend together. So the Teconics do run up and down along the Hudson Valley through here. The 5% error on here is that this map connects the Hudson Highlands to the Teconics. The Hudson Highlands are actually part of the Berkshires, the Greens. They're part of a mountain building period that is about 200 million years younger than the Teconics are. However, the southern Teconics do get caught up in the mountain building period that included the Hudson Highlands, the Housatonic Highlands, the Berkshires, the Greens. So I can see how the author made that mistake here. But we're actually looking at two separate mountain systems here, basically the Appalachians and the Teconics in through here. But so that's basically where we're going to start. And here's a much simpler map. Here's the Adirondacks again. Lake Ontario's out here, Mohawk Valley. Here's the Catskills, Long Island down through here. And the shaded color in here are the quote-unquote Taconic mountains. This makes it look like they're monolithic. They are absolutely not. But here we are seeing a separation between the Teconics and the Greens, the Berkshires, and now correctly, the Hudson Highlands. And you can see some of the shaded rock from the Teconics did get caught up in this mountain building period that made the Appalachians. So again, that map is more or less correct. What are the Teconics? Well, over here we see, it's very simple, folks. They're faulted and folded clipping of a nap with sedimentary and low-grade metamorphic rocks. And you're all saying, what did he just say? All right, let's break that down. Let's take it out of geologies and put it into something people can understand. This is what that map showed. Folded and faulted clipping of a nap comprised of sedimentary and low-grade metamorphics. Broken out, folded and faulted, bent and broken. Okay, we'll see that. Klippen is simply the plural of the word Klippe, German, which is an isolated rock unit, which is an erosional remnant, okay, of a nap. Oh, here we go again, a nap. All right, well, a nap is a sheet-like, out of place, this is important, rock unit that has moved on a predominantly horizontal surface. This is not vertical faulting, this is predominantly thrust faulting, predominantly horizontal plus or minus, but probably less than 45 degrees, okay? And it's made up of sedimentary, shale, sandstone, limestones, and low-grade metamorphic rocks. In this case, slates and a rock called a phylite, which is halfway between a slate and a schist. And so we have folded and faulted rocks, bent and broken rocks, erosional remnants of a big thing, an out-of-place rock unit that has moved on a faulted surface made up of shale, sandstone, and limestone. And when it's metamorphosed and the metamorphism increases from west to east, from the Hudson Valley, let's say, to the Mass line, that's what we're going to talk about, okay? And there's slates and there's phyllites. Well, what do we mean by low grade? Okay, this little diagram over here shows temperature increasing to the right and pressure increasing vertically. And you may not be able to see this, but it's 200 degrees C, 400 degrees C, 600 degrees C, 800 degrees C, and then 4,000 atmospheres, 6,000 atmospheres, 12,000 atmospheres. So these tectonic rocks we're going to be talking about up here in Western Mass, Eastern New York here, are way down in here. Low-grade rocks, these are about 300 degrees centigrade and about maybe 2,500 atmospheres, okay? So that's, well, 300 degrees C, that's not hard to visualize. 2,500 atmospheres is maybe 19 tons per square inch, maybe 38,000 pounds per square inch. Okay, so this isn't really all that difficult, but it was complex enough to just bedevil the bejesus out of early geologists. This is not simple geology. To understand this, we need to take a little step back in time. We're going back to the Cambrian. We're going to go back to about 540 million years ago. We're on Earth. This is the equator. And this is Proto-North America. And I know, it doesn't look right. Proto-North America at the time, Cambrian time, was rotated clockwise about 90 degrees. So this is Canada. By the way, light blue is shallow seas, dark blue is deeper water, and land is green and brown here. So this is mostly Canada. And what's going to be the United States? The outlines of the states are shown here. Montana, the Dakotas, Illinois, Indiana, Ohio, Western PA, Western New York, and then what? Well, this arrow says you are here. You're in the ocean. Shallow ocean anyway. New England. Where's New England? Where's the Maritimes? Well, they're not here yet. Give them time. They're coming. But right now, we don't have that. That land's not here. We're on the edge of the ocean here in eastern New York. Offshore, there's an ocean, a shallow ocean, small ocean, and then there's a line of volcanic islands, a Taconic Island arc. And separating this right off the now north coast of the Teconics is a deep ocean trench, like the Marianas or like the trenches you find in the Western Pacific. They're very deep water here, okay? A poor but not too bad analogy for this whole thing is China, the Sea of Japan, and the Japanese islands, okay? And we are back 540 million years ago. What's happening here on the surface of the Earth is this island arc is moving. It's moving northwards. And what's happening to the sea floor in between here? It's going down this trench. So as this moves this way, the sea floor gets pushed down this deep ocean trench and consumed out in through here. Let's move forward. Let's go forward about 100 million years. Okay, now we're up in the Ordovician, not that the word means anything, but we're 460, something like that. And that's first of all, North America is rotating counterclockwise. So this begins to look more like home. Montana, the Dakotas, again, Illinois, Indiana, a bit of Ohio, and this is so crowded in here you can't see it very well, but you are still here, right on the edge of the continent, right on the edge of what the geologists call a craton, if you want a fancy word. And the island arc here has moved in, and this sea has been consumed and been sucked down underneath this, and we're about to get hit hard. By the way, this is New England and the Maritimes over here, okay? So if we look at this in a little bit more detail, here's the, back to the Cambrian, now rotated into a more normal looking situation. So the US is here, Canada's here, the Taconic Island arc is there. If we look at this, the Grenville Craton is land, that's this. Okay, there's this shallow sea in here, that's this. Pennsylvania, New Jersey, New York. And then we have the Volcanic Islands out through here. The Volcanic Islands are here for the same reason that Japan is there, is that rock is being shoved down underneath it, melting and coming back up as volcanoes. In between, on the seafloor, coming off the land, we have very clean quartz beaches, very, very nice. Offshore, the currents are less and we have mud being deposited. We ended up with red and green shales. And then carbonate rocks, don't forget we are 30 degrees south of the equator now, so it's a good place to build a reef. Then out in the deeper water out here, which it's hundreds of feet deep out here, the currents are very slow. Only thing that's getting out here from sediment off the landmass is mud, black mud, which becomes black shale. And then we have the volcanic islands here, which I say are as a function of the subduction and the melting of the rocks. This is about 600 miles across at the time period we're talking about here. And remember that number. We'll come back to 600 miles much later on here. But basically, that's the setup we had here. And here we are in eastern New York. That's the Hudson River, theoretically. And here we are in eastern New York, and we're about to get punished. These cross sections are, again, highly schematic, but this is kind of like what we were talking about. In the Cambrian, we're pushing back, and here's the subduction zone going back this way. The sea floor under that shallow sea is going down here, melted rock coming up and spewing volcanic material over there. And we have this 600-mile wide or whatever thing. Okay, this picture is the Ordovician picture we looked at, and we're getting closer here, and we're starting to push up naps, slabs of rock that are moving more or less horizontally. They're not going straight up. They're being pushed in this way, one on top of another, like slices of bread. And then, ba-boom, we get hit. Here's the old continental crust that was up here. That's been metamorphosed now by this. The volcanic island arc has run right up onto the edge of the continent. The subduction zone is dead. And here we have folded rocks. Remember the folded and faulted rocks? In the naps, here's the naps with the little squiggles represent folds in here. And these are moving on these horizontal, quasi-horizontal lines, which are thrust faults. And this was about 540 million years ago during the Ordovician period. And it's this 440 million year date. That is the actual date that's used for the Taconic mountain building period, the Taconic orogony. Right? It's when the crunch actually happens. All this is preliminary, and yeah, it was going on for 100 million years. But this is the Taconic orogeny, and this built some serious mountains here, right where we are right now. You probably had mountains 10, 12,000 feet high. And then they sat. Okay, this ended, and things happened over here as we were beginning to bring in New England and the Maritimes. But for us now, the mountain building period is over at 440 million. and we got a big pile of stuff. This is a ridiculously simplified cartoon of what happened. Here's the west. This is the craton. This is not moving. Here's the east. This is the ocean. And we have layers of rock out in this shallow ocean basin, and volcanoes are out here off to the east. This rock is moving this way. Okay, the whole mess, this whole ocean is closing up, and it's going to be lost. And it's going to do this. Now, what's going to happen here? Because the craton is here, and it's your basic immovable object, these things are going to come pushing in here, and they're going to hit the craton, and they can't go any further, so they break. And you get faulting down through the nose of this thing, and this piece pushes up. By the way, oldest rocks at the bottom, this is like a layer cake, youngest rocks at the top. So this happens, ba-boom. Well, I don't mean ba-boom. I mean, it's probably, this takes tens of millions of years, but ba-boom in geologic time. And we do it again. This can't move anymore, so it breaks back here. And pretty soon this can't move anymore, and so it breaks back here, and so on and so forth, till we end up, like I say, like a bunch of slices of toast that you stacked up, each with the edge about an inch back from the underlying one. Here we end up with this, okay, and then this is the major crunch, and then we add about 400 million years of erosion, and we lose all of this. A lot of rock was eroded off of here. I mean, some of you may be familiar with the Schwangen conglomerate, the cliffs that are a couple of thousand feet of quartzite that are popular for climbing down on the west side of the Hudson Valley, south of us. That came off of here. All that stuff came out of here. The Tug Hill Plateau, that big high area out there west of the Adirondacks, that's sediment that eroded off of here. So a lot of sediment came off of here. And it was eroded down. It had time to do this. And so we end up with something like this. The Hudson River's over here, and then we have a stack going out towards the Mass border over here with New York. Notice something. What's happened here? The older rocks, the dark blue here, labeled 5, are all of a sudden, because of the erosion of this, they're on top of the stack. And the younger rocks are down at the bottom. This is what drove some of the early geologists back in the 19th century absolutely bonkers. This didn't get straightened out. It started in the 1930s, and it really didn't get straightened out until we got decent work done in the 60s and 70s, 60s really. And then we add a little more erosion. I mean, here's Route 22 going up in Berlin, and here, the oldest rocks, the Rensselaer Plateau. That's how we got more. I mean, it's okay, it's schematic, but that's basically how we got to where we are. All right. Here we have a complex looking thing. This is a geologic map. This is at the scale of 1 to 1 million. The Mohawk River comes down here. The Hudson River is right through here. The patterns and the colors on this bedrock geologic map represent the different rock types and the structure in the rock. I mean, this is the Adirondacks here, okay? And here's a nap. Here's another one. It's folded, but it's a great big, and that's 1 billion years old. We're working on something that's much, much younger than that. Over here, we have a whole bunch of isolated, remember that word? Isolated pieces of things. And I mean, that's obviously broken up. This one's in better shape. Okay, jumping over to here just for a second, we'll come back to this. Jumping over here, we have the Canberra Division boundary. We have 540 million when we're depositing the rocks out here. Sandstones, limestone, shales, and graywacke. Graywacke is nothing but a poorly sorted sandstone. It's got mud in it. It's got pebbles in it. It's got quartz. It's got feldspar. It's got pieces of other rock poorly sorted, okay? And up here, 440, that's when the crunch took place. So this diagram that we're looking at right here it's a stratigraphic column. And what it shows is the format, and we're not going to worry about the names or anything like that. It shows the oldest rocks on the bottom. It shows younger rocks on top, and it shows how they relate to one another. Okay, so now we're into the Taconic mountain sequence right here. And I don't know if you guys can read this down here. I hope you don't have to, but if you can, it's fine. This dark brown color is one of the youngest pieces, the youngest slices of these naps. And these are the clippa from the Livingston slice, all this dark brown. Now this is all one thing at once, okay? One big slice, and one of the younger rocks, but one of the first ones that got pushed to the west from the east here, okay? The yellow here is the Giddings Brook slice, and that's much more intact, although there's still dismembered pieces of it here and here and here and all that sort of thing. That goes from young to old. That rock was being deposited right through this whole shebang. And then over here we have, well, we're not going to worry about the Bird Mountain. That's way up here in Vermont. But anyway, and then down here, older, we have another series of slices shown in the dark green, in this, whatever that color is right there, the Chatham Slice, okay? And then the Greylock Slice in red here, not much left of it. The Everett Slice, there's more left of that. And the Austerlitz, and finally, down here at the very bottom, the oldest rocks, the Rensselaer Plateau. But if you look at this, it's like, well, wait a minute, that, like I said, the Rensselaer Plateau seems to be on top of everything. Well, in fact, it is, you know, topographically on top, but it is, in fact, the oldest rock, about 540 million years. These rocks are not easy to date. The kind of rocks and the depositional environments were not conducive to fossils and the preservation thereof, even if they were there, okay? And also, you can't radiometric date this stuff because to do so, you need minerals that formed while in the rocks, while the rocks were forming. If you radiometric dated any of this stuff, what you get is the date of the sediment that washed into the basin, not the date of the formation of the rock. So we have some fossil evidence, graptolites and the like, but we have rough numbers on this. We can do much better with rocks in the Adirondacks that are much older than we can with these. Anyway, another thing to look at here, you see these little black triangles that are all over the place? They're also on this dark brown, but you can't see them. But they're all over the place. This is a symbol geologists use for thrust faults, okay? And these are the thrusts that separated the naps, and they're everywhere. So you see, this isn't just one monolithic mass of tectonic mountains, and the Rensselaer being all of it. The Rensselaer is just part of it, of a much more complex system here. We're going to back off. Oh, yeah, I should tell you this. Remember I said we weren't going to talk about the stuff to the south? That's because the Teconics got caught up in the Alleghanian, the Appalachian mountain building system. That's much more complex. We don't want to go there tonight. So, same map, Albany here for location, and the same stratigraphic column here. And I'm just going to go through this quickly. The Livingston, bada boom, bada boom. The Giddings Brook, all of this. Okay, now I'm going to fly in some other ones. Okay, this is up in Vermont, the Dorset and the Bird Mountain, we're not going to worry about. The Rensselaer's here. The Berlin, we're going to have some look at that. We're going to look a little at the Everett and the Chatham. And of course, the Giddings Brook, yeah. But you see now, if you drive from Albany, you know, off the Mass Pike through here, you're going through a lot of different geologic units that unfortunately all look a lot alike, but never mind. If you, a well-trained geologist can tell the difference, right? Okay, and then finally the Dorset Mountain, yeah, okay, fine. This is a Google Earth image of, here, let's go back here for a second. Look at the shape of this, the Rensselaer Plateau, okay? This is a Google Earth image, Albany. This is greatly decluttered, but look at the shape here. That's the Rensselaer Plateau. That's made up of the Rensselaer Formation, which is graywacke and really resistant to erosion, but it is, as you all know out there, the Rensselaer Plateau is high, right? This is Route 22 coming down through here, and here we have the Berlin Slice over here, and the Everett Slice there, different slices, but this is our Rensselaer Plateau right through here, Route 2 going through there. We'll come back and look at that. There's that power line that cuts across the lower end of the plateau, but it shows up very nicely. It shows up because it's undeveloped, right? You guys all know that. You know, it's primarily forested land, so this is a lot of trees. That's why it shows up so well. But that's us. The scale down here, 10 miles. But that's basically what we're looking at here. Okay. So I said the title on this says is the Teconics are shifty mountains. Yes, they are. They moved. You saw the diagrams on this. You saw the cartoons. They moved. They were west of here, and they got pushed in here. And they're rootless. they are no longer attached to where it is they began life. Remember I showed that diagram that showed about 600 miles, about 1,000 kilometers of shortening. So if you had to, well, first of all right, we have to take away the Green Mountains. We have to take away the Berkshires. We have to take away the Hudson Highlands, take all that out of here. That didn't exist when this was forming. Okay, this is 200 million years later, and that we just completely discount that now. Unfortunately, I don't have a map that shows that. But the Teconics here are completely detached from the rocks where they were born. Okay, they were, if you unfold all of this, you come out about 1,000 kilometers, about 600 miles. If you had to point to where that root zone actually is now, it's actually on the other side of the Green Mountains and the Berkshires. Can you see this stippled pattern right through here? It's all folded up because the Appalachians happened. But this stippled pattern represents the area where the roots of these mountains were when they were stretched out 600 miles that way. So these are completely detached slices in through here. All of them are completely detached. Some of them are way out here. And they're moved. They've moved. Rocks underneath them and out in front of them haven't moved. These have been pushed over that, and I'll show you some of that too when we get around to that. But a little geotourism. I said the rocks were folded. You bet they are. This is over at the south end of Lake Bomoseen in the Taconic sequence there. These are basically muds and carbonate rocks. This is in the Indian River, a perfectly good, this is a slate formation up on the New York-Vermont border. And you can see the rocks have been folded here. Again, one of my students in there for scale. Students are so handy for scale. These rocks have been all folded up, and these are not small things, although I'll show you some smaller ones later. But the rocks are folded. They're thrust. This is the soul of the Giddings Brook up near Saratoga. These rocks behind the tree didn't move. These rocks are part of the Giddings Brook. They moved, and this is the surface that they moved on. Now, was it like this when they moved? Nay, it wasn't. It was flat or flatter, right? But this is, like I say, along came the Appalachians and messed with things again. So it folded the thrust surfaces. But this is the Giddings Brook. This is the rock it slid over. This is carbonate in this case, and this is basically mud. This is in the Giddings Brook just above the thrust surface down through here. And so it wasn't just the thrust surface that got deformed, but the rocks up in the slice. I mean, you're putting a lot of pressure on this when this thing is moving. These are hard rock thrusts. Originally, there was some talk these might be gravity slides or something like that. Nay, nay, nay. These are hard rock thrusts. There's also other interesting rocks in here I'm not going to talk much about, but the rocks that were falling into the shallow ocean basin were just tumbling down like falling Legos. And you got big chunks of rock falling into mud. There's a student's shoe for scale, never mind the hammer. And you have exotic blocks. This is mostly carbonate that's fallen into the mud in the matrix of the Taconic rocks. And this got caught up in the naps and got moved. And here's a big chunk. That's a 3x9 notebook inches for scale. This is a hunk of limestone that got caught up in here. This is mud all around it. So here you picture the stuff that was on the seafloor of that shallow sea. And here's chunks of rock tumbling down into it, probably stimulated by earthquakes. Because when you're closing an ocean basin, you make earthquakes. It's just how things are. And you made a lot of slate. This was mud. This is up in Granville. This is about 70 foot thick here, but this stuff is much, much thicker than that. This is actually a slate quarry. This is good quality slate up there. As you can see, this is nice and splittable, make shingles, make countertops and things like that. Very, very nice. All part of the Taconic sequence. And I mentioned volcanics. Well, yeah, you say, well, yeah, you had volcanoes. Where's the volcanic rocks? You know, not a whole lot of that got preserved as rocks itself. It got eroded away. Now, this is Stark's Knob. Contrary to popular opinion, Stark's Knob is not a volcano in and of itself. Stark's Knob is volcanic rock. And there are other pieces of volcanic rock caught up, even in the Rensselaer Plateau on the west side. On the east side, sorry, west of Route 22, there's half a dozen slivers of what used to be basalt in there. These happen to be pillow basalts at Stark's Knob. This is what's happening when the Hawaiian basalts are flowing into the Pacific Ocean right now, today. You get these blobs of rock forming underneath the ocean water. The lava flows in, it chills very quickly, and then the crust cracks and more of it blurps out and blurps out. But this is volcanic rock from the Teconics. It just isn't in where the place where it formed. The whole thing got moved over to Schuylerville. All right, so here we are. We're up on top of the Corning Tower, and we're looking northeast, Hudson River, obviously, and we're looking into, this is these hills and all this lowland here. This is the Gettysburg Slice, okay? The highland there that we can see, that's the Rensselaer Plateau, okay? So lowland, Gettysburg, they're not very resistant rocks. I'll show you some. I mean, resistant to erosion, okay? They're not hard rocks. The Rensselaer Plateau, let's look south. There's more of it coming down, whoop, there we go, coming down through here. All right, and you recognize that this is Albany here. Coming down, the Rensselaer Graywacke is very, very resistant rock. It is a marvelous construction aggregate. And we get down further here, looking into the Chatham and further south. Okay, now what we're gonna do here is we're going to take a little geologic drive through time, or not through space, I guess. Let me put this in. Here's the Mohawk and the Hudson, so to give you some idea of where we are. Okay, here's just Troy, Cohoes, Rensselaer, Albany be here, right about there, just to give you some idea. So I'm going to use this geologic map, which is slightly different in color, but not in information from the first one. The first map we were using, which showed all those slices and everything, was a 1 to 1,000,000 scale. This is a state bedrock map at 1 to 250,000 scale, so 4 miles to the inch, as opposed to 16 miles to the inch. But it shows the same information. But of course, just to be clever, because we're geologists, we had to change the color of everything. What was dark brown in the Livingston Slide is now this horrible green. And what was yellow in the Gettysburg is now this muddy brown. The Rensselaer was kind of a gray-green. Now it's this orangey color. I mean, if we made it all the same, then anybody could do this, and then where would we, the geologists, be? So we're going to use this map, Livingston Slice. We're not really going to look at much there. The Gettysburg, we're going to come over into the Rensselaer. We're going to drop south, and we're going to come up into the Chatham Slice. We're going to come up behind the Rensselaer, up through Route 22. We're going to jump up here on Route 2. We're going to come down and look at rocks over in here. Now, I got to tell you, folks, these are not really impressive looking rocks. I mean, I told you these were low-grade metamorphic rocks, and indeed they are, and they're not fun to look at. The Adirondacks were much hotter, buried much deeper, and are really, really pretty. These are kind of, yeah. I mean, these are kind of rocks that only a mother could love, but we're going to look at them anyway. So let's do that. Let's go through here. Oh, one more thing. Yes, look, if you can look at this very closely, and I'm going to have to get close to this. Some of these lines have these barbs on them. Remember I said those are thrust faults? And you see them everywhere, right? All around these thrust slices. You have other lines, like here, and like around this as part of the Gettysburg, and down to no barbs, right? These are normal stratigraphic contacts, where old is on the bottom, young's on the top. Here we would see it in normal stratigraphic sequence. In the middle of the Gettysburg, the brick color is older than the orange color, which is older than the green color there. That's a normal stratigraphic contact. That's what you see in most of New York. This plethora of barbed lines, these thrust contacts, are concentrated here in the east in the Teconics. Okay, having said that, am I ready now? Oh yeah, thrust fault contacts, I said that. Here we go. Our first stop in this virtual field trip is right over here in Cohoes. And we're going to take a look at rocks that are actually in place. This is the Austin Glen, you don't care. This is a sandstone, but this rock is not moved. This rock is in place, not badly deformed, and it was rocks like this that the naps moved over. Okay, they slid over this stuff, deforming the daylights out of themselves. But they really didn't do too much damage to this. This is the Hudson River. We're right south of the power plant in Cohoes. And it's here, let's get in closer. And you can see this is not badly deformed. It's not all shattered and chewed up. And it's a nice, relatively fine-grained sandstone. Good stuff. It's in place. Now we go across the other side of the river. And we're going to come over here. Again, there's the Hudson right there. We're going to come over here right to the edge of the Giddings Brook. And it's a mess. These rocks are right at the sole of the thrust fault, and they're shattered. They're destroyed. You can see just from looking this, can I go in? Yes, I can. These rocks have been badly, badly treated. It looks like two different rocks here, right? I mean, you got a light gray and you got a dark gray and you got a light gray and a dark gray. That's really the same rock. But here, the layering in the rock, the so-called foliation, not sedimentary bedding, the foliation of the rock induced by the deformation. It's a layering, but it's not sedimentary. Here it's vertical. Here it's vertical. Here it's quasi-horizontal. Here it's quasi-horizontal. So these rocks have been tightly folded. They're horizontal here, they're vertical here, they go back to horizontal, roughly horizontal there. You can imagine this stuff porpoising in and out of the surface of this. These are badly treated right at the western edge of the Giddings Brook thrust. And remember, we looked at big folds in the Indian River and stuff like that. Here's another one. There's a same 4-inch knife for scale. But here's, see it here going right around, there's a fold axis running right down through there. So the rocks are folded up and down, just like that. So they're these are also badly folded. You can see it out there to some degree too. These are badly folded rocks, and they shattered. And remember, our definition of the Teconics talked about faulted rocks too, not just folded. Here's a fault surface. It's the Canajoharie, but nobody cares. Here's a fault surface. Here, in this case, these rocks moved this way over these rocks within the nap. This is a fault surface right there. Those are slick insides if anybody cares. And these rocks move this way relative to these rocks down there. Backing out a little bit, that's the same fault surface. That's the fault surface right down through there. That's the same fault surface as this. And so these rocks went that way as they were being, this is west over here, as they're coming in through here. Very badly treated rock. Very difficult to geologically map. What you actually do here, you don't really map individual rock units as much as you map zones of deformation. That's doable all along up and down the Taconic front. Let's move deeper into the Giddings Brook. Now we're going to be on 351 near where across the 66 near the middle school. And we're into the Nassau in the Giddings Brook. And it is not in great shape. This was mud. It is now, well, it's shale, but it's thinking about becoming slate. It's thinking about it. No, it's not slate yet, but it's thinking about it. This is, as I say, the middle school is right behind us over here. This is the outcrop on the north side of 351. And you can see it's shattered up, and not nearly as bad as that Canajoharie was on the western edge of the Giddings Brook slice. And because I'm a complete idiot, I used a black knife for scale on dark gray rocks. I mean, it was just perfect. I don't know what I was thinking, but anyway, you're going to have to put up with that. So this is the Nassau in the middle of the Giddings Brook. This is what, like I told you, not real impressive. Not really good for much of anything. Now this is weathered, okay? This is on the surface, this is weathered. But this is the kind of rock that Troy Sand and Gravel is mining for crushed stone. And it's not really great stuff. They import other rocks to blend with this. Let's move into we were down here. Let's move up onto the Rensselaer Plateau. We'll look at the Rensselaer Graywacke, which is that dirty sandstone. Dirty, and by say dirty, I mean it's got all the mud still in it. It's got pieces of minerals, pieces of other rock, just awful. And here's a piece of it, right about 800 feet from my house. The Rensselaer is mostly a fine-grained rock, but it does have this coarse phase in it. And when I say it's got all kinds of things, these are pebbles. You can see it's a 4-inch knife or so. And these are pebbles that have been caught up in it. Normally, a rock like this would weather out. These are fragments of shale, this dark stuff. That would be gone in a heartbeat. The mud that's in here is unstable. That would break down chemically and physically. And all you'd end up with left is the quartz. Even the feldspar would be gone. Now what's cool about this stuff is if you step back, like you can see some of the coarse stuff here, and then it's finer. And there's the coarse stuff here. Now this is a boulder, okay, obviously. Obviously this stuff when it was laid down was rotated 90 degrees. So this is more or less horizontal. But what you're looking at here is you have deposition of this fine stuff. Then every now and then you get a mud flow. And then mud flow brings down this coarser, unsorted material into the basin, off the flanks of the volcano, probably not off the craton, probably coming right off the flanks of the volcano. Again, probably stimulated by either volcanic eruptions or earthquakes associated with volcanic eruptions, or just plain earthquakes. Okay, because they have coarse, and let me go in a little closer on this. Mostly this is kind of rounded, but not really. There's some angular pieces. There's some angular pieces. That's kind of rounded, so at least smoothed off, right? But it's not really well all-rounded stuff. How does stuff get rounded? It gets carried by streams and bumped around and bumped around. So some of this was transported by water and rounded, like this stuff. But some of it didn't get transported by water very far at all before it got dumped into the marine basin and then subsequently slid into deeper water, into where this finer grain material was being deposited. So that's both the coarse and fine Rensselaer Formation. Most of the Rensselaer Plateau, or what's left of it, this would have been originally about 2,000 feet thick. Now the Rensselaer Formation is like 800 or 900 feet thick, what's left of it. Most of it, and here we are, we're going to actually be on, I think it's Plank Road going off the crest down into Berlin. The crest is up here and Berlin's to our left. This is much more typical of the Rensselaer Formation. It's massive. It's very poorly bedded. It doesn't have fossils in it. There's that silly knife again for scale. But this is outstanding crushed stone. You want high friction aggregate, so cars don't slip on it. This is what you want. This is why Callanan and Valenti have those two enormous quarries outside of Brunswick. But you go up Route 2, starting to climb out of the valley and going up Route 2. Heading eastward there. There's both mining the same material. And this is the material also that Troy Sand and Gravel wanted to mine down in Nassau. And I don't think that's ever going to happen, but it's the same rock. This is outstanding material. And why is it so much better? Well, if you use carbonate rock for this, okay, I digress. But if you use carbonate rock, which we have a lot of in New York State, it tends to polish in the road surface and it gets slippery when it gets wet. Bad idea. Okay, and this is just a closing in. It's just a massive, massive, dirty sandstone. Okay, we were here. Let's jump south. Let's come down in here. And we are now south of Canaan. And we're going to look at a little bit of rock, this orange stuff right here, a little bit of rock that, again, is in place. These rocks, all these rocks with the barbs on them, slid over this. But this is the Stockbridge Formation on Route 22 south of Canaan. And this is a perfectly good, well, relatively low-grade marble. And it's a fine-grained marble. This is what Lee limestone, Lee lime is quarrying. When you drive east on the Mass Pike and you get over towards Lee, you drive on your right-hand side as you're driving east, you look into a quarry. This is the stuff they're quarrying. Again, this is quarried for crushed stone. But this is in place, and it's really not in bad shape. And we're going to go north now. We were down here. We're going to come back into the Chatham Slice. Remember, these are rocks that have been moved. The Chatham Slice was a nap, and all these remaining pieces are clippa of the nap. And we're going to come up here, a little bit north of Berlin, and we're going to look at this. Well, it was mud, but it's a little bit higher metamorphic grade, but it's still pretty awful. But notice, it's getting shiny. Why is it getting shiny? Metamorphic grade increases from the Hudson River eastward to the Mass line. And when metamorphic grade increases, meaning it gets deeper and it gets hotter, you get further recrystallization of the minerals. The clay minerals in the mud are turning into fine-grained mica minerals and reorienting parallel to each other. And mica minerals are shiny. So that's why this appears to be getting shiny. It's still deformed. You know, here you're looking at a flat into the surface. Here you're looking into the, and here you're looking into the edge of the surface. But it's starting to get a little bit higher grade metamorphism, not that it's really high grade, but it's starting to do something. It has a little ambition as a rock. And then we're going to come up here. Note the arrow points to a little bit of sliver of orange stuff, which actually is the same as the orange stuff we were looking at in place down here. So the star isn't where it is. We're looking right there along Route 22, north of that last outcrop. And here's a piece of the Stockbridge marble that is completely out of place. It got caught up in the faulting, and it's a lentil. It's now a lentil in the Nassau Formation, just an isolated block. You're looking at pretty much the extent of it right through here. But that that doesn't belong here. That's a piece of exotic rock that got caught up in the exotic rocks that were moving from east to west. And then now we are back into the Giddings. Now notice the brown here goes around and comes back down here, the color, right? This is the Nassau Formation we're going to look at again. This was Nassau over here, that horrible stuff that I said was trying to become a slate. Okay, that's what it looks like over here. So that Nassau Formation goes all the way under the Rensselaer Plateau, from here under the Rensselaer Plateau, under the Rensselaer Slice, and it's the same rock we see over here. Okay, and the Rensselaer sits on top of it. And so it's also not really an impressive rock. You can see it's got this planar characteristic to it, and that dark knife again. It's not really a decent slate. This is not quarryable slate. It's more than shale, but less than slate. And now here's Route 2, Petersburg Pass up here we're in. And we're going to up into the Berlin Slice, and we're going to look at the rock there. Now here, we are actually getting into a halfway decent rock called a phylite, Phylite. And this is a low-grade schist. This is beyond slate. This is really starting to reorganize the minerals and grow bigger minerals in here. And again, it's just manifest by the fact that you've got really shiny rocks over here, and then you have dull looking rocks. Here, the foliation, the layer in the rocks is vertical or quasi-vertical. Here, it's quasi-horizontal. So it's catching the sunlight and reflecting like a mirror. Here, it is vertical and not doing that. And finally, we're coming down here to the Everett Slice. And we're going to look, this is on Route 20, just outside Lebanon. And over here, you go into Hancock Shaker Village. And now we're into a true phylite. This is right at the crest. The hiking trail is over here to our left, our right rather, and so is Hancock Village. And this is a good-looking low-grade schist or phylite. Again, vertical foliation here. I've turned this block so I'm looking into it. It's very shiny. You can see this very easily as you drive by there. Okay, so this is the highest grade metamorphic rock we have, and this is to the east of the Rensselaer Plateau. Now, in this little inset map, that star is right where we were just looking at the Austerlitz, and we're going to look, see the arrow? We're going to look off here to the west. That's this view we're looking at here. This is Route 20 down here, Lebanon, and Lebanon Valley is out through here. We're looking into this yellow, that's the Chatham Slice. Low rolling hills, and it's all very nice and very pretty, particularly this early in the morning. If we turn our eyes and gaze northwestward, which we do here, oh, that's the Chatham Slice, I said that. All right, we turn this way, and we're looking now northwestward instead of westward. That's the Rensselaer Slice and the Rensselaer Plateau right there. Kada bing, kada boom. You're looking right into this edge right here on the Rensselaer Plateau and the Rensselaer Formation. There she be. And if we move northward, back up to Petersburg Pass, Route 2 is down there, and we look at, again, you see the look direction here? We're looking at the northern end of the Rensselaer Plateau, right out there. We're looking across this brown Giddings Brook mush, and if you look really, really hard up in here, you're looking over into the hills of the Giddings Brook back there over the Chatham. And frankly, if the weather was clear, you'd see the Adirondacks out there as well. The Rensselaer Slice, the Giddings Brook Slice, and we're looking over the Chatham Slice. And now we're looking out again over the Chatham, there's the Giddings Brook out there, the Rensselaer's back here. So it's a complex package of rocks that make up these Taconic Mountains, of which our Rensselaer Plateau is just one single piece. And now to finish up and to return to a point I made in about the third slide, I said the Teconics in the Berkshires, when you look at it on a satellite image or something, they look like all the same thing. Well, there's a reason for that. We're standing here at the probably near the summit of the pass, and we're looking north-northeast, and we're looking into entirely Taconic rock out there. If we turn about 90 degrees and look to the northeast, those are the Berkshires. So the Teconics and the Berkshires are jammed right up against one another, such that unless you know what to look for in the rocks, you don't notice that you're actually driving through two separate separate mountains and separate mountain building periods separated by about 200 million years. And that, my friends, is the end of it. This book is out of print, but still available. This was, Don Fisher was the state paleontologist I used to work with, and he produced this. This is much more than just the Rensselaer Plateau, but it's not bad if you're interested in reading this sort of thing. And with that, I'm done. And I think I talked plenty long enough. So I'll toss it back to you, Jim.
All right, thank you, Bill. I see one question in the chat at this point, which is Claudia asking, what's the difference between Phylite and Greywacke?
Okay. Let's look at the starting materials first. Phylite starts off as mud. And I mean mud, the stuff that squeezes up between your toes. That's the starting material for that. If you turn that into a rock, squeeze it. Don't metamorphose it, just squeeze it. It's going to turn into shale. And the shale is going to, if you squeeze it some more, is going to turn into slate, which is good hard stuff. You know what patio slates are. So that was mud turned to shale, turned to slate. If you put more heat and pressure on it, you get the phylite. Okay, now you're recrystallizing the clay minerals and you're making micas. All right, and it's shiny. The Greywacke starts out life as a pile of gravel and sand and mud. It is unsorted. A well-sorted equivalent of this is a sandy quartzite beach, sandy quartz beach, right? Everything is gone. All the things that can be dissolved by chemical reactions are gone. All the things that are soft and can't stand up to being banged around are gone. You just end up with a well-sorted sandstone. Greywacke is the entirely opposite of that. It's everything just dumped into a pile. So it's rock fragments, it's sand, mineral fragments, it's mud. Okay, you take that and squeeze it and you get, as I said, a dirty sandstone. In the case of the Rensselaer Formation, it's also been silicified. That water containing dissolved silica has moved through it and it's kind of gluing it together, but it doesn't, a Greywacke really doesn't have to be silicified. So on the one hand, you've got a sandstone, on the other hand, you have mud. And if you increase the pressure on the two of them, from the mud, you get the phylite through stages, and from the sand, you get a Greywacke if it's a dirty sandstone. I hope that helped.
All right. We have one from Mary asking, what's the simple way to answer the question, how is the Rensselaer Plateau separated from the Teconics? Is it the same rock or age?
What was the same rock or?
Age.
Age, yes. Same rock, no. You notice as we went through this, we kept talking about different slices. Those are all, as an aggregate, all those slices, 8 of them, are referred to as the Taconic Mountains. Okay, and the Rensselaer is one of those slices. The Rensselaer Plateau, the Rensselaer Slice, is one of those 8 slices. So the Rensselaer Plateau is part of the Taconic Mountains, right? But as you saw, as we kind of perused through this quickly, there's a lot of different kinds of rock in the Taconic Mountains in the different slices. So it's all more or less the same age. Let's call it 440 million. But, well, I'm sorry, the Taconic Mountains are 440 million. The Rensselaer Formation as part of the Taconic Mountains are actually older than that. So different rock types, the individual slices are different ages, but the Taconic Mountains themselves are referred to as one unit of a 440 million year age. But basically to comprise the Teconics, you got to have all those slices. And we're just one part of it, a very resistant part of it, but part of it.
All right. I don't know if this is a geology question or not. I'll ask it in case it is. Does anyone know how Buck's Corner at the intersection of Plank Road and Dutch Church got its name?
Okay, I'm going to pass on that, other than somebody shot a big buck. Or somebody named Buck lived there, more likely. But no, I don't. That's not geological.
Okay. So we'll maybe try to find the answer to that another time. So let's see. How does the rock on the plateau affect the type of soil and vegetation on the plateau?
The rock doesn't so much. It's the glaciation that does. The thing is, we are so close to the last glaciation, we really haven't developed any kind of weathering that gets down pretty much to the rock surface, particularly up where we are. I mean, it's true that let's say you were in Georgia, or actually even Southern Virginia, the rock is weathered all the way down to the bedrock, and the components of that bedrock, the chemistry of that bedrock affects the soils, the chemistry of the soils and the mineralogy of the soils. The ice went out of here 12,000 years ago. And all we've had time to do up here is have a 10 or 12 inch soil horizon developed on the glacial till, right? So if you don't try this, but if you were to dig down to bedrock with a shovel, you go through the soil horizon, you go through some weathered glacial material, and then it'll be all till, really, really hard till, till you get down to the bedrock surface. So in general, up in the Teconics here, and in particularly where we are, the soils are developed upon glacial materials, not so much influenced by the bedrock. If we let this weather for another, I don't know, couple of 100,000 years, 100,000 would probably do it. We would have weathered the tills down and start to get into the bedrock. But right now, our soils are glacial soils. Now, the soils can be different because the glacier deposited sand here and mud here and glacial till there. So yeah, you get sandy soils and muddy soils and awful, rocky soils. But that's a function of the glaciation, not the bedrock.
Okay. John asks, I have seen some black shales off exit 11 in Malta. Are they related to any of the shales or slates you showed today?
Malta. No, those are going to be, okay, those are in place. So that was the stuff that Teconics slid over. Age-wise, they're not that far apart. And a black shale, and black shale is a black shale is a black shale. So some of the rocks in the Teconics that we looked at were black shales. They're a little bit metamorphosed and screwed up now. So they started out with the same parent material, mud, marine mud, as a matter of fact, and of Ordovician age. But the Malta stuff is in place. The stuff in the Teconics got moved. I guess that's the simplest way to do it. But other than that, yeah, black shale's a black shale, and not really good for much of anything. But then again, I'm biased.
Okay. I think I could almost answer this one. I'm not sure. What caused the frequent and many boulders at the surface in the Rensselaer Plateau?
Yeah.
Mountain area. Are those glacial relics, and how did the bedrock contribute to this?
Yes, they are glacially transported and they are glacially deposited. Somewhere that rock had to be broken off of bedrock, carried by the ice, and deposited here in the Rensselaer Plateau. That was north of us. Now, we don't really have a good handle on the pre-glacial topography of the Taconic Mountains, or the Rensselaer Plateau for that matter. But when the ice moves from north to south, as it first invades an area, it's going to go across areas with cliffs, with steep mountainsides, and that stuff, the ice is going to break that stuff off, and it's going to start carrying it with them, right? And it would carry it down ice, down current, if you will, and deposit it. But of course, it wasn't that simple because we had 4 periods of glaciation in the last 1,000,000 years. So each glacial period breaks off rock, moves it, drops it, melts back, another glacier comes in, breaks off rock, moves it, picks up the other rock, moves it, drops it. We do this 4 times. And like I say, the ice went out of here about 12,000 years ago last. So somewhere to the north of us, some of it as far away as Canada, some of it up in Vermont, and some of it probably within tens of miles. That those rocks originated as bedrock and then got picked up and brought down here. But it's you go to any sand and gravel pit around here and look at the rocks, and what the hard rocks that could stand being moved by the water, the glacial runoff, they're mostly Adirondack rocks, because everything else was just too soft and got broken up. Those black shales in the Nassau Formation, the Canada, they wouldn't last 15 years being bounced around in a river. So yeah, it's the resistance stuff from the north that got down here, and the ice moved some really good sized rocks when it was at it.
Okay, let me see if I can read this one without tripping up. Peter asks, though more of a superficial geology question, were there any major shaping events by the past glaciation in the Teconics? We have major erosion at places like Mohawk Falls and the depositional areas into glacial Lake Albany. But what about these higher elevations?
Probably smoothed it, picked up everything that was loose on the surface of it and carried it off, either to the south or it washed out of, a lot of the present topography you see is actually formed by runoff, water running off from the glacier melting, like the sediments out in glacial Lake Albany, like the deltas, like for instance, the beaches, Route 4, down by Home Depot and running up in Detroit, runs right along the old beach. That's outwash, that's running out. The valleys around here, like the Tassawasset Valley, for instance, are filled quite deep with cobbles and boulders that washed out of the ice, but it was the water that was doing the work. The ice itself although it'll pick up anything it can move and it'll break off bedrock where it can, isn't really that erosive. If there's rock, either in the form of things the size of a potato or the size of a car, caught up in the soul of the glacier, that's a pretty good tool, and that'll carve in to the rock. But that generally makes pretty fine-grained sediments. So the glaciers will pick up material, they'll deposit material in moraines, but the moraines that's Long Island. We don't really have recessional moraines that are well defined here in the Teconics. We have them well defined in Western New York, several recessional moraines, but we don't really have them. They're not really well defined here at all. So the ice moved stuff, water ran out of the ice when it melted, redeposited stuff. So the ice itself really isn't all that abrasive.
Okay. I saw a partial question come in and I asked for some clarity.
I can say start video. Nope. I got nothing on this now. Oh.
I think next time we should get the speakers
Let's
set up.
see. Okay, I'm going to try to piece this together. The Rensselaer sandstone where I live in Cropseyville shows a few examples of angular fragments mixed with fine-grained rock. Could you comment on the mechanics?
Yeah, okay, yeah, I know, I can envision what you're talking about. You were primarily depositing fine-grained material, fine-grained sand, muds, silts, and that can be moved by relatively gentle currents, either gravity currents coming off the highlands, coming off the beach, if you will, highlands, or actual currents in the ocean moving, or the shallow sea moving this around. To get that coarser material you're talking about, the pebbles and things, you need a period of, and it can be very brief, but you need a period of higher current flow, more energetic water flowing. Right, so it can pick up and move bigger things. And so when you see larger, pebbles the size of a ½ inch, either in layers or individually, in the fine-grained stuff, something happened. a flood, a hurricane, something, you know, increase the velocity of the water so it could carry those pieces. Or the other possibility is a mud flow. I mean, this coarser grain stuff, it can only be carried by the water off the land just so far, and it gets dropped. And it gets dropped and it gets dropped and it gets dropped, and it's likely to build up an unstable pile. It's okay in normal conditions, but in a hurricane or with a volcanic eruption or something shaking the ground, it's going to let loose. And this stuff can go, you know, down the slope and into the deeper water where normally you would just deposit mud. So you need higher velocity water. You need some kind of a slump, a mud flow, a stronger current for a while, something to move the bigger pieces into where the smaller pieces were being originally deposited. And then when that current stops, whatever it is, you go back to depositing the fine grain stuff again. And the coarser grain stuff begins to build up again closer to the shore.
All right. Thank you. I think that's the last question I saw. So thanks so much, Bill, for coming back again to do this. We now have a recording of you that we can share.
Am I going to make the cover of the Rolling Stone?
I don't know. We could work on that, but.
All right. Well, I'm happy to do this, folks.
What are you talking about? The geological stone or the, yeah?
Yeah. Anyway, you're entirely welcome. I'm glad I can help you out. And have a nice folks. I'm going to go eat lobster, as a matter of fact.
Nice. And I have seen a lot of thank yous go by in the chat too. So.
Okay. Well, that's great. Okay.
Thank you so much.
I'm glad you enjoyed it. Good night now.
Take care. Good night.
And
Good night, Bill. And I would just say, yeah,